Good morning. Thanks for having me. My name is Sergio Luna. I am a PhD student from Mexico, and here I will present the progress of my research project with the topic Invasive Species Distribution Models are strongly influenced by the choice of the calibration area. As an introduction, I would like to start by mentioning that biological invasions represent the second leading cause of biodiversity loss worldwide. Once established, invasive species are often difficult to eradicate. Considering this, a faster response will usually have greater cost benefits. Therefore, it is essential to identify those species that represent the greatest invasion risk to justify effective management measures. Currently, there is a large amount of biodiversity and environmental data. The integration of this information associated with the ecological niche concept has resulted in the development of correlative modeling methods to infer species distributions, known as ecological niche models of species distribution models. In the case of invasive species, a paramount consideration is transferability. Models may have the ability to produce good predictions within the range of values where they are calibrated, but their accuracy might decline beyond this domain. Here we can see the relationship between accuracy and transferability across different groups, where model performance usually decreases in the exotic range. However, it is possible to obtain models with good accuracy and transferability, as we can see here. To ensure the usefulness of models for conservation purposes, it is essential to explore the factors that influence the model transferability. In this study, we assessed the relative importance of four factors that influence the performance of invasive species distribution models using virtual species simulation. For this purpose, our methodology consists on the simulation of species native and invasive ranges, modeling the species native and invasive ranges considering different modeling aspects, and evaluation of the performance of these models. Virtual species were simulated using the bioclimatic variables from WorldClim, restricting our study area to the American continent. These variables resume information on precipitation and temperature with a resolution of 2.5 arc minutes. We followed the methods of Warren and coworkers with some modifications. Using the virtual species R package, 2 to 5 variables were selected at random to define the species niche using the two principal components of the environmental space. Here is an example of a species with these three variables selected. This niche was projected across the study area to define the environmental suitability, which was then converted to an occurrence probability using a logistic function. To define the native and invasive ranges for each species, we programmed a cellular automaton to find possible areas where the species will be at environmental equilibrium. To accomplish this, each species was assigned a dispersal capability at random, with possible values within the 50 to 250 kilometers, which for this example is 124 kilometers. Using this information, an accessible area was simulated as shown here by selecting presence points with Bernoulli trials based on their occurrence probability, generating buffers around it with a radius equivalent to the dispersal capability, and iterating this process until the point of environmental equilibrium, where the area does not increase. Up to 5 areas are searched, and one is randomly selected as the native range and one as the invasive range. Here we can see the process repeated for 3 accessible areas. From this native range, 100 occurrence records were selected with a probability equal to the occurrence probability times the magnitude of the sampling spatial bias, which was simulated here using the Human Influence Index dataset. A total of 100 records were selected from this process. This process was repeated 5 times for each species to account for stochasticity in the sampling process that could over or underestimate the evaluation metrics. A total of 100 species were simulated to account for different sampling bias, dispersal capacities, physiologies, and geographic extents. Here we can see 6 of those species. Niche models were built using Maxent from the Dismo package, with the different levels of the 4 factors set out here. The effect of the extent of the calibration area was evaluated by sampling the background within a radius of 25 to 1000 kilometers around the occurrence records. The effect of dealing with the predictor collinearity was evaluated by calibrating models using all available variables or by removing variables with a Pearson correlation higher than 0.7. The effect of dealing with the sampling bias present in species datasets was evaluated by filtering occurrence records, especially with a maximum distance from 0 to 20 kilometers. Finally, regularization multiplier is a value that penalizes the use of additional or complex parameters in order to avoid overfit models. The effect of this factor was evaluated by using values from 0.5 to 5. Each model was calibrated using only native occurrence records and evaluated according to its predicted accuracy in the native and invasive range. In both cases, the true model performance was defined as the Spearman-Rank correlation of the true occurrence probability and the suitability values predicted from Maxent, which we term functional accuracy. The relative contribution of and relationship between the examined factors were assessed through linear models using the LMG method implemented in the Reline info package. Additionally, discrimination accuracy was calculated using cross-validation, partitioning the data into 4 groups randomly and in geographic blocks, using the voice index as the evaluation metric of one randomly selected group. We included an unbiased model for each species, considering a scenario where the ecological characteristics of the species are well understood. A total of 200,000 models were evaluated. Here are the results obtained from the native area. Each point represents a model. The functional accuracy is shown in the y-axis, and the x-axis represents different species. Different replicates are shown with a different color. The unbiased model for each species is denoted with a plus symbol, and the red dashed line represents the expected value by chance for each model. Unbiased models showed excellent performance, with a maximum value of virtually 1, a minimum value of 0.56, and a median of 0.97. Normal models showed higher variability in their performance. Maximum functional accuracies across species varied from 0.99 to 0.18 and a median of 0.9. Minimum functional accuracies varied from 0.7 to minus 0.96 with a median of minus 0.26. These findings highlight the significant range in model performance between species. 30 species showed models with only positive accuracies, while for 13 species, most models had negative accuracies. Here is shown the explained variance by the 4 factors evaluated. The box plot summarizes the distribution of this percentage for all species. We can see that the greatest effect in the native range was because of the extent of the calibration area, ranging from 2 to 93% and a median of 51. In the invasive range, the extent of the calibration area also contributed to the highest explained variance, although it was less pronounced, ranging from 0.7 to 67% and a median of 18. This is in concordance with some previous study. For example, Van der Waal and coworkers reported lower performance for models calibrated in either too restricted or wide regions. Similarly, Warren and coworkers found the highest level of functional accuracy for the largest buffer analyzed. On the other hand, Lobo and Tornelli found that the location of pseudo-absent points does not affect model performance. And Fernandez and coworkers reported that buffer size accounts for only 3% of the explained variance. The regularization multiplier was the second factor, but played a less prominent role, with a median of 3.7% of the explained variance in the native range and a median of 3.3% in the invasive range. Predictor collinearity and spatial thinning of the occurrence records showed virtually no impact, contributing with a median explained variance of less than 1% each one. although for some species they account for almost half of the variability. Here we show the relationship between the model functional accuracy and the discrimination accuracy for all species. Functional accuracy is divided by the extent of the calibration area, and discrimination accuracy is divided by the partitioning method used. Overall, we can see that the correlation is positive for larger calibration areas in both partitioning methods, and also that larger calibration areas led to better functional accuracies. In conclusion, it is possible to obtain models with high functional accuracy within the native area of the species. But the functional accuracy decreases in the invasive area. That is, the models are less transferable. Even so, there are models with a high functional accuracy in the invasive area. The extent of the calibration area had the greatest impact. Overall, better performance is related to larger calibration areas. In areas for smaller extension, performance decreases with high values of the regularization multiplier, that is, the less complex models, while as the extension increases, the effect of the regularization multiplier is smaller.